All right, so a steady-state temperature problem in spherical coordinates. Take a moment to write this down. The object in question is a hemisphere, so half of the upper half of the sphere. And one of the conditions, let's say, is that the flat bottom is kept at temperature 0. So this will be our homogeneous condition. And let's say the exterior of the sphere, the round exterior, is kept at temperature 1. And suppose that the radius, and remember, in this case, we assume that the temperature depends on the radius r and the angle theta. And remember, the angle theta is measured from the positive z semi-axis, clockwise like that, downward to the negative semi-axis. So if you have a full sphere, remember, it's going to be 0 and pi, right, the domain for theta. In this case, it's a hemisphere, so theta will go from 0 all the way to pi over 2. Especially when you have word problems, make sure you understand clearly how these coordinates are measured. So let's say that the radius is c, like I put here on the picture, which means r is between 0 and c, and theta is between 0 and pi over 2. Starting from 0 and pi over 2. So remember, theta equals pi over 2 identifies the bottom, the flat bottom of the sphere. So the flat bottom kept at temperature 0 means that u of r pi over 2 must be 0. Again, r varies, right? So the whole flat bottom, but theta is pi over 2 to identify just the bottom of the object. And if I want the temperature to be 1 on the exterior, I formulate that by saying u of c theta equals 1. So you fixed c so that you are just on the surface of the sphere, and then theta varies to take into account the full cover. This will be the non-homogeneous condition which you deal with at the end. Obviously, I choose one to make the first example as easy as possible, but really it can be any function of theta, right? So that's the whole point, right? I mean, because at the end you're going to do superposition principle and all that good stuff. Now, we're not going to do all the steps we did before. Remember, the starting point of the steady-state temperature is to set the Laplacian equal to 0, which in spherical coordinates, in terms of r and theta only, that looks like this: 1 over r times u differentiated twice with respect to r, 1 over r squared sine of theta times sine of theta u partial theta, and the whole product partial theta, again equal to 0. So look back on our first lecture on Legendre equations and look at the steps involved in separation, and that leads to two equations, one in theta, which ends up being our modified Legendre equation. So that's going to be sine of theta h prime of theta prime plus lambda sine of theta h of theta equals 0. Boundary conditions, sometimes you don't have any boundary conditions, but in this case we have a homogeneous boundary condition. And that comes from separating this guy here, right? So this is going to be r of little r times h of pi over 2. That implies big H of pi over 2 equal to 0. So this will be the Somerville problem to solve first. The equation in R will be of Cauchy-Euler type. That's r squared r double prime, big R, plus 2 little r, r prime, minus lambda r equals 0. No extra condition on this one. And like I said, we're going to deal with this at the end after superposition principle. I want to make a pause here for a moment, because when I say no boundary conditions can sometimes are assumed on the Somerville problem, this is because of the physics essentially and the shape of the object, if you want. So let's take a pause just to relax a little bit and just go back to the physical meaning of the problem. What's a steady-state temperature problem? It's a situation when as t goes to infinity, the temperature doesn't change anymore, so it stabilizes. So if that happens in an object, what do you need to know to identify the solution, which tells you what's the limiting temperature on each point? Well, obviously, you need to know basically what happens on the boundary of the object. Now, notice if you have a full sphere, the entire boundary of the object will be a single condition because it will be identified by something like this, you know. So u of c theta equals some function of theta, right? I mean the temperature distribution on the exterior. You don't need anything else, right? Because you assume that the heat flows along the radius and then with respect to theta, because the boundary again of the object is given by a single condition. Now when I take the half of the sphere, things are different a little bit, because now I have the boundary of the object, the physical boundary, given by two different shapes. I got to tell what's the temperature on the exterior, and that happens to be a non-homogeneous condition in this example. But then I have to say something about what happens at the bottom, and that introduces another condition here, which in order to solve it, I made it homogeneous. If it's not homogeneous, remember we have tools to deal with non-homogeneous conditions, but this is why you have now a condition like this in the case of a hemisphere. And by the way, if I said instead of being kept at temperature 0 that the bottom was insulated, all of a sudden you'd have had a derivative here, which led to the condition H prime of pi over 2. So with this digression, let's move back to the problem. We solve the Somerville problem first. Based on the discussion we had before, we know that given this boundary condition, h of pi over 2 equals 0, the eigenvalues will be the pair starting with the odd numbers. So 2n plus 1, 2n plus 2. And the eigenfunctions, h2n plus 1 of theta, will be p 2n plus 1 of cosine of theta. So these are your eigenfunctions. You can actually skip this big H, just write it directly, p2n plus 1 of cosine of theta, because these are your eigenfunctions. And remember, always n goes from 0, 1, 2, and so on. What do we do with the method of separation of variables? Doesn't matter if we have Bessel function, Legendre equations, doesn't matter what type of Somerville problem we have here. Once we identify the eigenvalues and the eigenfunctions, we solve the other equation, the other ODE, for each, so solve for each eigenvalue, lambda. And then at this point, you can call the solution R2n plus 1. By the way, the index, once you identify that the index is always an odd number, call the index is always 2n plus 1 to be in agreement with the assumption that all of these coefficients are odd. Okay, so let's plug in lambda. So we have r squared, r double prime, plus 2 little r, r prime, minus 2n plus 1, 2n plus 2 times big R equals 0. Remember how we solved the Cauchy-Euler equation. And if you don't remember, pause for a moment and look for the formula for the solution, for the characteristic equation. The coefficients in the Cauchy-Euler equation recipe are 1, 2, and minus 2n plus 1 to n plus 2. Remember, it's very important to do what I just told you, to actually stop and look it up. Because if you don't process it through your brain, what happens here is not going to stick. So there's no rush. Slow down as much as possible. As much as needed, I mean. So the characteristic equation of the Cauchy-Euler equation, I'm going to denote by S, because I can't use R, right? R is the radius in the sphere. So the characteristic equation of the Cauchy-Euler equation in this case will be AS squared, which is going to be S squared, plus B minus A, which is 2 minus 1S, plus C, which in my case is 2n plus 1 minus 2n plus 1, 2n plus 2. S squared minus S minus 2n plus 1, 2n plus 2 equals 0. Okay, lucky us, this actually factors nicely. Because these are consecutive terms, you can actually take one case, let's say s squared minus s minus 2 times 3. This always factors into s minus the smaller one, s times plus the bigger one. So you could actually use just trial and error to factor these guys. You can use the quadratic formula, but it's an overkill if you do that. So pay attention here that with these coefficients, you always have this factorization. S squared 2n plus 2 times s minus 2n plus 1 times s. Let's see, s squared plus, I think I made a wrong sign here. Sorry about that. S squared plus s minus this. And yeah, that's the factorization. There's a plus between s squared and the second term. So the two roots are 2n plus 1 minus 2n plus 2 minus quantity 2n plus 2. So, and I'm going to continue maybe here. Keep this here, and then let's continue on the left side. So the solution for big R, and again notice I index that by 2n plus 1, will be some coefficient a2n plus 1. The variable of the equation is little r, so r to the power 2n plus 1 plus b sub 2n plus 1 r to the power minus quantity 2n plus 2. Notice all the indexes, I call them 2n plus 1 because you go through only the odd coefficients all the time. So that's the solution for r for each lambda. We don't have any extra conditions, but remember the solution should be continuous on the interval of interest, and because r can approach 0, we need to have b2n plus 1 equals 0. So due to the continuity assumptions, we must have b2n plus 1 equals 0. Because otherwise this will go to infinity. And with that being said, you're left with a 2n plus 1 r to the power 2n plus 1 right before imposing the what we call it, the superposition principle. All right, so what is the superposition principle? Means that we have a solution u of r theta in the form of a series from 0 to infinity involving r to n plus 1 that we just found times the eigenfunction p to n plus 1 of cosine of theta. So I'm going to rewrite it. I'm going to write actually this on the, yeah, let me write it again on a new piece of paper. I don't want to make another part and break the flow. All right. So we have that this is the format of the general solution. The left thing to do is to find a2n plus 1, and that will come from the remaining condition to impose, which is u of c theta equals 1. At this point, things should be familiar as a technique, right? I mean, you plug in c for r, so u of c theta. So r becomes c, which is the radius. This can be an actual number in some other problems. P to n plus 1 of cosine of theta, this should be equal to 1, or whatever the function in theta you may have in the problem. So this is the moment when you say, okay, to determine a to n plus 1, I need whatever is the right-hand side, in this case, 1 as a function of theta. I need 1 as a Legendre series in the polynomials p to n plus 1 of cosine of theta. So you need a Legendre series involving the odd polynomials. And then you identify the coefficients. So let's say you don't have a table of formulas and you have to find these series by hand. Then you go back to the formula for the Legendre series in terms of odd polynomials in terms of cosine of theta. And what does that say? The formula says that 1, your function, follow that formula, it's gonna be let's see, so you want let's see, so let's actually write it differently. So this coefficient, yeah, I mean, it's not just a2m plus 1. That's another thing to keep in mind. The coefficient of the odd polynomial is together with c to the power 2n plus 1. So a to n plus 1, c to the power 2n plus 1, which will be the coefficient of p to n plus 1 cosine of theta, needs to be matched with whatever is the coefficient of 1 when you write it in terms of the Legendre series. So you write 1 as a Legendre series and in terms of these polynomials, and the coefficient of the Legendre series, which comes from a formula, will be matched with the coefficient of p to n plus 1 on the left. And that's how you actually determine a to n plus 1. So this entire thing will be the Legendre coefficient, which comes now, and now you apply the formula, comes from 4n plus 3, the integral from 0 to pi over 2, your function, which in my case is 1, p to n plus 1 cosine of theta, sine of theta, d theta. So that's applying strictly the definition, right, of the Legendre coefficients. So what do you do if you have to solve the integral by hand? Well, you always, in this case, make the substitution x equals cosine of theta, which will bring this into the standard, in terms of the standard Legendre polynomials. So this will be equal to 4n plus 3, the integral from, now it's going to be between 0 and 1, p to n plus 1 of x dx. Now, on the previous lecture, we actually did this. We computed the Legendre series in terms of the odd polynomials for the constant function 1. And the answer for that, for this coefficient, was minus 1 to the n over times 2n factorial over 2 to the power 2n plus 1 n factorial squared 4n plus 3 divided by n plus 1. So we did that in the previous lecture. Using those recurrence relations, you could solve the integral, and that's the answer. Okay, so we're finally close to the end. A to n plus 1 comes from solving from it when you set this equality. So a to n plus 1 divided by 1 over c to the 2n plus 1, the right hand side. And you can stop here. Remember, once you find the coefficient, you can stop. If you want to write the full solution, just to have it in front of you, obviously plug it back into the summation. A to n plus 1. We can rearrange the terms a little bit here, so it's minus 1 to the n to n factorial 2 to the 3n plus 1 over n factorial squared 4n plus 3 over n plus 1 1 over c to the 2n plus 1. That's just the coefficient. Continue with what you have in the series here. What I meant is over here in the solution. So times r to the 2n plus 1 p to n plus 1 of cosine of theta. So that is the solution for the steady state temperature. And as I said before, we often are happy to give the answer of the coefficient in terms of Legendre polynomial is evaluated at 0, for example, so you don't have to necessarily come back with the actual factorials, I mean the explicit formula. So I'm not going to make a third part, although this will be a little bit longer than normal. I just want to point out how things will be different. For instance, if you have a different boundary condition, if you go back to the problem we had here, let's see, to begin with, let's say, like I said before, let's say this was an insulated bottom. So this will be prime. Then the only difference is that you're going to have 2n plus 1. And so this will be p2n of cosine of theta. So basically, when you're doing the last step here, you're looking for a series in terms of the even polynomials. Now, if you don't have any other boundary conditions except the non-homogeneous condition, let's say if you have a full sphere, then of course the eigenvalues will be all n times n plus 1, and Pn of x or Pn of cosine of theta will be the eigen functions. We'll go over other examples. So from this point on, let's consider the theoretical part of it over. And a couple of lectures that follow up from here will be just other examples and some hints on the homework, which I'm going to come up with later in the week. And with that, that's it for today.